If the light started on this side, it would go to this focal point. And so the lens has two focal points, not just one. However, let me draw a mirror again. Maybe I'll draw the fun mirror with it. Here's the concave mirror. The concave mirror only has one focal length, but it also has one center of curvature. And so if you remember that discussion from chapter 17, we were paying close attention to these 2 points, and we will do the same thing. And so I will say it again, that the lens really isn't much different than the mirror. But there are a few things that we just label different. See, we don't have a center of curvature. We actually have 2 of them. 2 focal lengths as well as 2 center of curvatures. But we don't care about the center of curvatures. We care about the focal length. Also, even though when we did the mirror, we said, well, the mirror had only one focal length. And although that is true, if you remember our drawing, we put an object out here, and even though there was one focal length, we kind of treated it like it was 2. Didn't we do this? Didn't we say a beam coming in, and I did it in red, so where's my red one here? I said a beam coming in would hit the mirror and go through the focal point. In other words, I thought about the focal point after the reflection. And the other one was to say it goes through the focal point before the reflection and then goes straight, making an image right here. And so even though we only had one focal point, I treated it as 2, one before hitting the mirror and one after hitting the mirror. And I will say, I'm going to do the same thing here with the lens. Let's ask this question. If you put an object in front of a lens, where is the location of the image and how big is the image? And I will draw using both focal points just like I did in the last chapter. So let's give it a try. Let me grab my black marker here. Let me come over here. Let me draw a lens. And in particular, let me call this a convex lens. Let me put a dotted line down the center. I'll call that the optical axis. And as I just emphasized, let me put a focal length on both sides. Let me put an object in front of the lens. Let me call H sub O for the object height. Let me call the distance to the object D sub O. And let's draw the rays. And I'll start in red. What would happen to a ray that was going parallel to the optical axis when it hit the lens? Well, that was the whole point of showing you this. That one going straight would bend. Now it would bend twice. It would bend going into the glass and it would bend again coming out of the glass. But those 2 results together go right to that focal point. And then it would bend a little bit, and then I don't know how to bend it twice. Bend it here and bend it again. And so I guess it would look something like that. It looks like 2 bendings. But the effect of both bendings would send it right to this magical point, the focal length. And of course, then it would continue on. And I'm hoping that drawing looks like what I did on my first drawing for the concave mirror when I drew this one hitting the mirror going through the focal point. And then the second ray I'll draw would be this one. See, this one goes through the focal point first and then hits the mirror. So let me come over here. Let me draw one that comes through the focal point first and then hits the lens. What will it do? Well, it will go parallel. So there'll be a little bending here and a little more bending there. So technically there's bending twice. But the overall effect is it would make it go straight. And that's the reverse process. And so like we said for the mirrors, the law of incident, or the law of reflection, which says the angle of incidence equals angle of reflection, we can draw those two rays. I'm saying the same thing, that if you do the rays in reverse, you get the parallel one. And so then my object, or my image would be right here. And so the distance from the lens would then be called the image distance. And so I'm using the same terminology. In fact, going through this a second time, I hope it helps you if you didn't quite get it the first time when I did it with the mirrors. Now I'm doing it with the lens. And notice what I have here. Notice that I have an image that is upside down, it is smaller, and notice the light really hits here. So I would call this the light really hits here. So I would call this a real image. This is exactly parallel in thinking to this. Upside down and smaller and real image. And not a surprise, the equations I get are going to be exactly the same. How about I work them out? Let me grab my green and blue markers here, and let me grab a set of triangles. If you remember, the first set of triangles I drew in blue, and I said let's take the image and project it into, now we did the mirror last time, so let me say take the image and project it into the lens, and let me draw then a set of two blue triangles. Let me convince you that those two blue triangles are similar. These are vertical angles, so they're equal. These are right angles, so they're equal. And once you have two angles equal, the third has to equal, because the sum of all the angles of a triangle has to be 180 degrees. And so that's my proof that they have the same angles. And if they have the same angles, they're similars. And so this right here is the height of the image. From here to here is the focal length. That means this distance would be the object distance here, that's this whole thing, minus the focal length. And so if I set up my first equation in blue, I would go the height of the image is to the object. So height of the image is to the object as the focal length is to this distance, which is object distance minus focal length. And so just like I said in the last chapter, if you had a question that says, hey, I have an object that is, out in front of a convex lens, or out in front of a concave mirror, you're going to use the same equation. This is exactly the first equation we got for this fun mirror. It's exactly the same one we get for this convex lens. And if you wanted to know how high the image was, you just have to be knowing the focal length and that's a terrible D, let me fix it. And you just have to know the object distance. So usually in a problem, they give me the object distance and the object height. For a lens, they usually give me the focal length, and they ask for what is the height of the image, and that'd be a perfect equation for it. Well, let me try the green marker here. Because if you remember, the green one that we did was to take the height of the object and put it in last chapter we said put it in the mirror, project it in the mirror. Now I'm saying project it into the lens. And then if I make this set of green triangles here, where this is then the height of the object, and if this is the image distance, then this distance right here would be image distance minus, this would be focal length. This would be image distance minus focal length. And so my green similar triangles would look like this. The height of the image is to the object as the image distance minus focal is over the focal. And maybe I should have done that in black. But if you go back and look at your notes or the video, you'll see this is the same equation I got back in the chapter 17, that I could use this if the object distance is greater than the focal length. Now, let me emphasize, this would be true for the convex lens. So I guess the good thing is I don't have another set of equation. This is good for the convex lens and the concave mirror. Now, we could, as we said, have a mirror, or a lens, excuse me, where the object is closer than the focal length. And we did that same thing with the concave mirror. And we got a slightly different equation. So let's work it out again here. I'll take my markers and move down to here. Let me come over here and say, all right, what if I had something that looked like the following? Let me just dry the board here and say, all right, what if I had, here is my convex lens. Here is the optical axis. Here is focal length on one side and focal length on the other. Let me put my object at some point that is closer than the focal length. And let me draw the rays in red here. The easy one is the one that goes straight. It would bend twice and go through the focal point. That was the whole idea of the focal point. Now the second one's a little harder to draw, and it was the same way for the mirror. Because if I draw one from the object through the second focal point, it never goes to the lens. So what I need to do is to draw one that is coming from the object to the lens, but the one I want to draw is the one at the same angle as if it was coming from the focal point. Because when this one hits the lens, and I almost made my lens too small there, it would go parallel. And so somebody standing over here would say, all right, this beam goes into my left eye, this beam goes into my right eye, where do they appear to be coming from? And if you trace this ray back, it appears to be coming from here. If you trace this ray back, it appears to be coming from here. And so there is your image. And since the light really didn't come from there, this would be called a virtual image. And notice then that if this is the height of the image and this is the height of the object, notice I have an image that is upright and bigger. That's exactly what I said, and I better go kind of quickly here with time, but that's exactly what we said for this concave mirror, that if you are within the focal point, you can get upright and bigger. And so the equation I'm about to derive is actually the same equation that we got for the concave mirror. And so as I try to derive it here, let me put some numbers here. This would be the distance of the image. This right here would be the distance of the object. If I try to make a blue triangle, the blue triangle would be to take the height of the image and put it into the lens, and I would get a set of triangles that are embedded inside of each other. And so I'd have this small triangle right here, where the bigger one here is the height of the image, and this one here is the height of the object. So if I wrote out the equation, I would say the height of the image compared to the object, image to object, would be this distance, so that would be focal length, over this distance, and this would be then the, this distance would be what? Focal length minus object distance. So focal length minus object distance. And if you remember, we had this discussion with the concave mirror that they came out almost the same. It's just that the bottom here was switched. And so sure enough, you see the same equation. And if I make a set of triangles in the green, then the green one would look something like this. Why don't I project the height of the object into the lens and then make a set of embedded green triangles that look like this. And if I do the big triangle, so I have the height of the image is to the height of the object. So this is to this. As this whole distance, and so this whole distance would be this, which is focal length, and then this, which is image distance. So focal length plus image distance. Over this, which is the focal length. Now let me just double check that. So height of the image is to the object, okay, as this whole distance, which would be focal length and image distance, is to this distance, which is focal length. Okay, good. And that should be the same equation. I can't remember now quite what that equation was. I want to wrap this up so we can say, okay, we're done with the chapter and you can do the test here. I'll put a box around this. And so this box then would be the magical equations that you would use if then your object distance is less than the focal length. And this would be true for the convex lens. And it's also true for the concave mirror. Both of those should be. And so I should go back and look at that equation. And I think that was right. I can't remember. Do you remember if we got that same equation before for the concave? I'll have to go back and, something's bothered me about it, so I hope it is. I'm going to double check that one. Well, let me just double check right now. If I put this into here, and this line would go. What is this line? Yeah, this is the line where it appears to be. Okay, I think that's right. And then, oh shoot, and I've gone over time here, so why don't I just real quickly then point out with a little quick demonstration here that if I took these other two, that is the convex mirror and the concave lens, they have the same overall effect. Watch, here's the mirror that hits it and spreads it out. Here it hits it and spreads it out. And in this case, it would look as if the light was coming, if you trace this back, maybe right about there. And so this line coming back, this line coming back, and 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 this line coming back. If I take away that and maybe just block all these, you can see that they all look like they're coming from a magical point, which again we'll call the focal length. And if you'll let me erase that one and switch it around, it's true no matter what direction you go through this lens. You can go this way and it spreads out, and it spreads out the same way if you turn it around. And so just like I was saying earlier that the convex lens we can label with a focal length on each side, it doesn't matter which way the light goes. For the concave lens, the same is true. It doesn't matter which way the light goes. So we put a focal point on both sides. So if you let me change this drawing, I'll leave a focal length on both sides and change it to a shape that is concave and then puts concave. And that concave then would mean that if I put an object out here and I drew a ray, so let me make a optical axis, and to maybe real quickly finish this up here, where's my red one? Draw a ray. The ray would hit here and bend outward as if it is coming from right here. And the other one would be heading towards this focal point and would have kept going and hit that focal point, but bent and went straight. And if you then imagine that this is the light that goes to the left eye and this is the light that goes to the right eye, and you trace that one back and you trace this one back, you're going to get an image right here. And it would be a virtual image because, again, it appears to have come from there. The light didn't really start from that location. In other words, the lens did not make the light converge to a point and then spread out from there. That would be a real image. And so this one was the real image. But this is a virtual. But again, that's exactly what we saw for the concave lens. The concave lens was always doing the same thing. That's why I called it the boring lens. It always made things smaller. And it always made them right side up. And maybe I've got some lenses here, but maybe it's just a good place to stop. I'm not sure. You know, I was going to get closer and say, okay, if I have a lens like this, maybe I could put it in front of something, and this is the concave, and so maybe by putting it in front, maybe you can see that everything on the other side of this lens is upright and smaller. Whereas if I jump back to here, but I'll get close, so I guess it'll be more like here. I'll get within a focal length. Everything here would be upright and bigger. Now, this one too, maybe that one's got too much magnification. Maybe I should use this one. This would be bigger for the camera. Everything here should be upright and bigger. But if I was far away, and I don't know if I can get the angle right between the camera, so I'll just give up and say, then it should be upside down, and either bigger or smaller, depending on how it worked out. Well, since we're out of time, I better call it quits, but I do want to say I didn't quite finish the equation here, but go back and the equation we had for the convex mirror, and so that I guess I will put up here, what the equation here for the concave lens and the convex mirror are the same. And so maybe the trickiest part of this optics is to pay attention. Are you talking about a mirror or a lens? And then what shape is it? Is it a concave or is it a convex? And then where is the object located? Now, where it's located will not matter for the concave lens or the convex mirror. There's only one set of equations. But for the concave mirror or the convex lens, we have one set of equations if we are further than a focal length, and we have another set of equations if we're closer than the focal length. And so that's probably the hardest part. That's why I wanted to draw these and see where they came from. But once you know, do I have a lens or a mirror? Am I closer or further from the focal point? That's when you can then say, all right, now I know which equation to use. And in this case, you don't even have to do the geometry. I've just done all the geometries, maybe except for this last step. And so you've got those geometries. I would even encourage you, between the time you see this, which will be later today, and the test, which is tomorrow at 11, you write each of these equations on a notepad right next to you so that you can then say, okay, do I have in this problem a convex lens or a concave lens? Or do I have a mirror? And so, do I have a mirror, do I have a lens? Is it convex, is it concave? Is it closer to the focal length or is it further than the focal length? And then you can decide which of the equations to use. And then the question will just directly say, what is the height of the image? What is the location of the image? Those are the hardest ones. And so, as I said, I think the hard ones for this whole semester really are the geometry, and that's why I went through it. Now that I've done the geometry, now I would say I think those are pretty easy. You just got to be careful on asking yourself, do I have a lens, do I have a mirror? Is it concave, is it convex? Is it closer than the focal length or is it further than the focal length? All right, well, better call it quits now because I think the power is going to go off. And I want to get all this stuff put together, and we've had a lot of troubles with it. I just want to get it sent out. In fact, I'm going to work on this and have Ron work on it before we do the lab, because I'm not sure how much time it's going to take in the lab, because that's where most of the water problem is. And so we're going to work on that next. But I'm going to send these out first, and so it'll be a little different than normal. I'm not going to do the lab and the lecture together. So you won't know that till you get it, but you're going to get the lectures first. All right, call it quits, and good luck on the test. I will see you in lab in maybe an hour or two, depending on how things work out around here. Bye now.